All right, are we complete? Can we start?
Yes.
Yes. Right, thank you. So my name is Bernhard. I'm part of the Mono Runtime team, and I joined Simran 4 years ago, and since 3 years we are part of Microsoft. I will talk about Simran, Mono Runtime a little bit, and then I will mostly talk about Apple mobile platforms, and then I will also have a war story on Simran Android at the end of this talk. All right, so let's start with a little bit of history. This is the Simran engineering organization 3 years ago that was at the last Evolve. And this happy guy in the green shirt is Miguel Diacaza, and he is the founder of everything here. So he founded the Mono project in 1999, so it's 20 years old now. And he wanted to bring the .NET platform to the Linux platform. And he wanted that because he also founded this other project called the GNOME Desktop. And he wanted to enable developers to write the applications in C#. And he thought that's a smart business idea, so he founded a company that was called Ximian, and it was quickly acquired by Novell. And together with SUSE, which was also owned by Novell back then, they tried to push the Linux desktop in the enterprise sector, and you can probably guess how well this went. So they got laid off a couple of years later from Novell. But while being at Novell, they started to work on this other thing where they tried to run C# applications on the iPhone and Android devices. And back then, this was a bit of a risky idea because people said, oh, the future will be HTML5 apps on the mobile platforms, and going native apps is crazy, you shouldn't do that. Luckily, it turned out different for us. And so Miguel and his friends founded Simran. And as we all know now, it was acquired by Microsoft. So that's kind of the short history of Simran.
Success story.
Yeah. All right. So Alexander already talked a little bit about what Simran is. For me as a Mono Runtime engineer, it's essentially a bunch of C# bindings for native APIs to iOS and Android. As you can see, the slide is very old. There's also this Windows stuff in there, which I think was for the Windows Phone. It's not true anymore. And so the idea is that you don't have 100% code sharing, but that you can share essentially business logic, but then the platform-specific code is still per platform. But there's also this other thing, Simran Forms, which is essentially just yet another abstraction layer on top of it. So you have this XAML language where you can describe your UI elements, and then you have 100% code sharing. All right, so this is Simran. That was the sales pitch. What is the Mono Runtime? So the Mono Runtime is a .NET virtual machine, and virtual machine in the sense of that it executes .NET bytecode. So there's this ECMA specification that defines what the .NET bytecode has to look like. And as you probably all know, .NET bytecode comes from the C# compiler, so we don't directly execute C#, but we execute .NET bytecode. And there's one obvious approach how you can implement that, and that is JIT compilation. So the idea is that the Mono Runtime starts up, it loads the assembly, it looks up the main method, and then it compiles that bytecode from the main method into machine code, and then it will execute it. And as soon as the main method tries to call another method, the JIT compilation kicks in again, and it will compile all those methods that are needed lazily. And this is different to what you have, for example, when you have a C program, you use GCC or Clang, and then you compile your whole program, and then you have an executable, which is called offline compilation. There are advantages and disadvantages for each mode, and that's why we also have an ahead-of-time compiler, which is essentially this offline compilation. So you can pass an assembly to the Mono Runtime, and it will compile each method into the assembly and will store it into some image that can later be loaded by the Mono Runtime. All right, we have two different modes for that. I will talk about that a little bit later. And we also, since 2 or 3 years, we also have an interpreter, which is a bit counterintuitive because usually an interpreter is simpler to implement than a just-in-time compiler. So you usually would have that first, but we had other reasons for the interpreter, which I will tell you in a second. All right, and we support a bunch of platforms. So historically, we support Linux, and it was kind of straightforward to port it to macOS. Since we're part of Microsoft, we also support Windows properly. We kind of have to. And then we also, BSD, and then we have community contributions to support mainframe OSs, which, it's very esoteric, but there's this one guy, and he loves it and submits patches, which is great. Then, of course, those mobile platforms, which I will talk about later. We also support consoles, and we have all this kind of diverse support for architecture. So, AMT64 and x86 is kind of what you have.
Speak out.
Louder?
Yeah.
Oh, sorry. Okay. So that's what you usually find on the desktop or laptop. Intel and AMD CPUs. Then ARM v7 is ARM 32-bit, which you usually find on low-powered smartphone devices or on older smartphones. And ARM v8 is ARM 64-bit, what you find in, higher-powered smartphones these days. And PowerPC again is a bit more esoteric, and the same for S390X. Anyway, the latest addition is WebAssembly, which Alexander already talked about. It's pretty cool. All right, so what else is special about the Mono Runtime? We have this so-called Embedding API. And so traditionally, when you think about when you're on a Linux machine, you have the console, the shell, you type in mono, and you pass the assembly. That's how you usually would run a .NET program. But with the Embedding API, you can link the Mono Runtime into your application. So let me give you an example. Let's say you build a game in C++, and you have this amazing game engine, and now it's time for making up a story in this game, and you don't want to write the story in C++, but you like C# for some reason. So you can use the Mono Runtime embedded in your game, and then pass .NET assemblies to it, and it will execute this kind of stuff. And you can also build an interface to your C++ application, so you can actually talk to it somehow from the C# world. And that is used by game studios, like as I said in my example. And Unity is another huge user of this embedding API, but they go a different route. They actually allow you to write your whole game in C#. Then there's Blazor, which Alexander mentioned before. And now to close the circle, another big user are we ourselves. It's Xamarin Android and Xamarin iOS. So if you think about Xamarin Android, it's really just a Java application that embeds the Mono Runtime and runs C# from there. That's kind of the idea. All right, so I'm doing most of my work is in the Apple world, so I will focus more on the Apple stuff. So who of you has used Xamarin iOS for the iPhone or iPad? Okay, a couple people. Okay. So it was the first mobile platform by Apple, and they have two architectures that we care about on the devices. So it's ARM 32-bit and ARM 64-bit. And we have these two execution modes. The one is called full ELT, and the other one is the same plus LLVM, which I will explain on the next slide. And on the ARM 64, devices, we also have an interpreter, which I also will talk about later. But there's also x86 and EMT64, and what is that? So everyone who has done any iOS work will probably know that there's an iPhone simulator, and that iPhone simulator is really a simulator and not an emulator. That means it's really targeting another architecture. So when you ask the tooling for iOS to build the app on the simulator, you will get a completely different binary than for the devices. And also the restrictions they have on the devices don't apply to the simulator. And that means we can just use a Mono almost in the same configuration as on macOS or Linux. So the simulator is kind of trivial for us. But what is difficult for us is are the devices. And that's why we need full ET. So what is so complicated about the devices? On iOS, they have this security limitations, or for whatever reason they have that, they do not allow cheat compilation. So what does that mean? That means you cannot allocate memory that is writable and executable at the same time. And that's needed for a JIT compiler. You need to write machine instructions into it, and then later on you want to execute it. And so I mentioned before, we have these two kind of modes of ahead of time compilation. And the first time when we started to work on EOT, we did it just to improve the startup performance on Linux. And the way it works is that we only compile, like, we don't compile 100% of the methods of an assembly. We only compile the methods that we can easily do ahead of time. And the problematic case here are generics with value types, which I will have a slide for that, why this is complicated. So we have these two different kind of modes. And another thing that we also have is trampolines and wrappers. So a trampoline is like a snippet of machine code instructions that are needed to glue together stuff in the runtime. And in the normal EOT mode, we would just generate them at runtime and essentially JIT, so we cannot do this on iOS. And therefore we need to include all those things in the EOT image to make it work on iOS. Another side effect of this is that it means we cannot support system reflection.emit on iOS. Took us some time to educate our users to not use it, yeah, but I think you got used to it. And yeah, another thing is that in this EOT compilation process, we can plug in LLVM. So LLVM is a compiler framework that is probably known for C compilation. But they have this nice interface where you can put LLVM IR into it. And so we have a mode where we can generate LLVM IR, feed it into the framework, and get nice machine code out of it. And they do a really good job with low-level optimizations, and that's good. But they don't solve everything magically for us related to performance, because, for example, LLVM doesn't understand high-level concepts like object allocations. They just don't know how to handle that. And there's another disadvantage for like when using LLVM in Mono, and that is compilation time. So in theory, you could use it in the JIT as well, but the compilation time is very slow, so it really only makes sense to use it when you EOT compile. All right, so what about generics? Why is it so hard for iOS? So let's look at this method. It gets some T and then it returns some T. Essentially, there are three cases now. So the first case is T is a reference type, so for example, a string. And for me as a compiler, it essentially means it's a pointer. And so when you emit machine code, there's something that is called calling convention that you have to respect. So the pointer argument is coming in some specific register, and also the return argument needs to end up somewhere in a specific location and so forth. And so you emit that kind of code for reference types. And this can handle all kinds of reference types because they're all pointers. And the other case is that it's, for example, an int. And int specifically is almost the same as a pointer. It uses the same registers in the calling convention. And in this case, you could share it. But what if t would be a floating point, so a float or a double? The calling convention there is different, so there are specific sets of registers for floating points, and you need to emit a completely different kind of code. And what if it's a user-defined value type, so some struct in C#? It can have any size, and this is kind of hard to handle, like any size. So what we do in the JIT is, for each instance of t, we would generate a different method, and we would just, do that. So for full EOT, one approach you could do is that you try to do a closed world analysis where you try to find all possible instantiations of t, and then you emit code for that. But that can lead to code explosion and blow up your EOT image size, because in theory there's a lot of constructs that can happen that lead to a lot of possible instantiations. So you really don't want to go there. So we have something else. We have something that is called generic sharing for value types. And the way it works there is that everything is passed as a reference. And we also inject a hidden argument at the end. And this hidden argument is essentially a descriptor about the current t. So for example, the descriptor will tell me the size of the current t, and then I can use memcopy to copy from the argument location into the return buffer. And this is a bit of magic. So let's assume we have this call side, which calls with an int 5, and it also obviously expects an integer as a result. The way it works is that we first go into a trampoline. So this is the magic machine code snippet, and this argument trampoline will inject this hidden argument. And then we have another trampoline that will allocate the buffer for the argument. It will allocate the buffer for the return value and does some other stuff. It will also handle, when the callee is returning, it will also handle the case that it will put the value in the return buffer into this I variable, which should be in some register according to the calling convention. So it's kind of complicated, and as you can probably guess, there is some performance penalty doing that, but it avoids the code explosion. All right, any question?
So it's not a good idea to use it on your REPL?
We don't have a REPL on iOS. Not yet. We'll come to that in a second. Yeah, well, it's that slide actually. So for those guys who use Xamarin iOS, have you ever seen that? Okay. that would happen when you try to use system reflection.init. You will get this exception telling you, hey, you cannot use JIT compilation, and it's not allowed. Well, it's not true anymore, because we have an interpreter. So initially the idea was to enable system reflection.init. That's what we can do now with the interpreter. Another nice side effect is that it will fasten up the inner depth loop. So unfortunately in Xamarin iOS we don't have incremental compilation. So that means as soon as you do one line of change in your source code, you need to kick off the EOT compilation for this whole assembly again. And this will take some time. When you don't use LLVM, it will take a couple seconds, but it's a couple seconds, right? And also the other side effect is when you don't need to use the EOT compiler, you don't have the EOT image, so it means you will have a smaller app bundle, and that means you can upload it faster to the device. So this whole inner dev loop will be fastened up a little bit. And we also have this mode, which is called mixed mode, which allows you to use both. So you will then have an option where you can select which assemblies should be EOT compiled and which should be interpreted. And you can even go so far that you say, just EOT compile everything, and when I'm using system reflection.emit at runtime, it will use the interpreter for that. So we now can have a REPL on iOS. And this is not part of Xamarin iOS yet in the stable release, but there's a preview available for trying out if you go to blog.xamarin.com. And the interpreter also ships on WebAssembly. So. All right.
Quick question.
Yeah.
Is the interpreter also coming to Blazor, or
I'm sorry?
do you know if the interpreter is also coming to Blazor?
Well, we use it on WebAssembly, and Blazor is using our WebAssembly port. So the default configuration is to use that interpreter. Yeah, it was kind of a funny story because we initially started the interpreter for iOS, and it ended up in WebAssembly first. So that's how things work. All right, so the next platform in the Apple ecosystem is tvOS. Has anyone used Xamarin iOS to develop for tvOS? Yeah, I thought so. And it's kind of the same as iOS, but there are some little buts. So for us as runtime engineers, this is kind of important. So on tvOS, Apple doesn't allow you to use inline assembly anymore. And this is specifically when you have a garbage collector and you do this stop-the-vault thing. You want to get a precise view of everything on your CPU. And that means you want to get the register content, and for that you need inline assembly. So we cannot use that anymore. But there are some APIs available that you can use which give you almost the thing that we want. And garbage collection is happy with that, so that kind of works. Then they also tried to push something that requires you to ship your apps when you publish them to the App Store with bitcodes. Bitcode is this intermediate representation from LLVMs. And the idea there, I guess, by Apple is that they can recompile your app with further optimizations or do some security hardening, like adding that or whatever. But we found a workaround, so we could just embed our own generated code into some byte array and ship that, and it worked. So it required a little bit of hacking in the tooling, but it worked. It still works today. All right, that was kind of easy. But then there's also watchOS. So has anyone used Xamarin iOS for the watch? No. Has anyone the watch, the device? I've seen a couple. Yeah. No one develops for it, but yeah. Anyway, we also have support for the watch, and there are two different devices. So there's the ARM v7, so it's ARM 32-bit, which is the Series 1, 2, 3, and then the Neo Watch, the Series 4, is kind of a weird device. It has a 64-bit chip in there, but it uses a 32-bit ABI. So what does it mean? That means the pointer only has 32-bit, so they don't use the upper 32-bit. There are some advantages, some disadvantages to that, but it's a weird decision because there's no one else in the world doing that on ARM. Anyway, yeah, there's also the simulator. Okay, so on the watch, again, they don't allow inline assembly. But in addition to that, they also removed that API that we used as a workaround on tvOS. So we have another workaround now, which is even worse, but it kind of works. Since we don't have that many users, it's not that much of an issue. We have a lot of workarounds. another big thing for us was that they removed the signal on Cisco. So you might know signals from when you ever have done C or C++ programming, you probably got a segmentation fault at some point, and that's a signal that is sent from the operating system to your application. And so in languages like C# and Java, you have a lot of objects and you have like field access and whatever, and they can all throw a null reference exception. And what you can do as a compiler, you can insert an explicit null check. So you insert an if pointer is null, then throw this exception, and otherwise do the actual field access. But there's a trick, and that involves the segmentation fault. What you can do is you just emit the field access and you don't do the null check. And if the pointer is actually null, then you will get a segmentation fault. And now the Mono Runtime has a chance to handle this segmentation fault and can look up where the segmentation fault is coming from. And if it's coming from a managed method, then Mono will turn it into a null reference exception. Well, so we cannot do that anymore in WatchOS. It's a performance penalty. We can just insert those explicit null checks. But it also affects other things. So if the segmentation fault is not coming from managed code, it's probably a crash in the runtime, and then it would kick off crash reporting, which would give us Mono developers some more additional information what happened. We cannot do that on the watch. It's a bit sad. Then there's also some other stuff, thread suspension. I will not go into that now. But essentially we used signals to let threads to communicate with each other, which we also cannot use anymore on the watch. All right, and again, they forced this bit, or they tried to force the bitcode requirement, but this time they did it properly. So we cannot embed our code into some byte array anymore. And now we really have to emit poor bitcode. And the problem is, although we have LLVM support, which is kind of the thing that they want, the technical debt that we did in the beginning, because we didn't know that WatchOS will happen, is that we forked LLVM. So we have our own LLVM version, which adds a couple of Mono-specific stuff. So for example, it will emit unwind information, so we can do exception handling and other low-level stuff. And the problem here is that Apple wants bitcode that is compatible with their LLVM, and we don't control their LLVM, so we had to change a lot of things, which also meant a lot of performance penalty. But since we don't have that many users, performance is not much of an issue. It's more like it should work, but everything else doesn't matter that much. All right, that was iOS and Apple. Any questions so far? All right, so Simran, Android, I don't have much to say about it because I didn't work much on it, but as Alexander already mentioned before, one of the key problems there is that you have two garbage collected languages. So you have the JVM and you have the Mono Runtime. And as I said in the beginning, Xamarin is essentially a bunch of bindings to the APIs. So on Android, it's bindings to Java API. And when you request something, some, I don't know, UI element, it's a Java object, you will get the reference, and then on the Xamarin side, you will have a C# object that holds that reference. And when there is a garbage collecting GC event happening in the Java VM, it will not see the C# object. So we have to do some magic. We call it GC bridge, which lives on the Mono side. So simple said, it will allocate a dummy object in the JVM that kind of has a relationship with the object in the C# world. All right, but I have some war story to share. It happened on the Samsung Galaxy S7. And there were like a lot of things happening that were not good, like on the technical side and on other things. So the first thing that happened was that we announced the acquisition from Microsoft and Simran. So that was not a bad thing, but I will explain in a second why I mention it. 2 weeks later, the Galaxy S7 was available to buy, and another 2 weeks later, we got the first bug report that when you execute an app written in Xamarin Android, it will, like with a 50% chance, fail with crash with that exception. And so what we usually would have done back in Xamarin is that I would go to my boss and ask him, hey, I have this bug, can I buy the device? He says yes, I go to Amazon, buy it, get it 2 days later. Oh, sorry. And it's night mode. And everyone is awake again. So I would just buy it on Amazon, get it 2 days later, have it on my desk, can reproduce the bug, and I give the receipt to my boss and he will give me the money. With the Microsoft acquisition, it was a bit more complicated because we were not really part yet of Microsoft, so we had some stops of budgets, blah, blah, blah. And, you know, it's very complicated. So we couldn't do that. It was a bit of a shitty situation because, like, at least, I don't know, 5 times a week we got another user confirming this issue on this device because the Samsung Galaxy series is very popular apparently. All right, so we are 5 months later, and now, you know, the acquisition is done. We can get devices and everything. And a coworker got the device. He's located in Boston, and he couldn't reproduce it. So that was a bit weird. And then it turned out Samsung ships 2 different kind of Galaxy S7, and I don't mean the smaller and the larger one. I really mean it's different per region. So in the US, they ship with a different CPU than in everything, you know, in Europe and Asia and so on. I guess the reason is related to the radio, you know, LTE and whatever. It looks a bit different in the US, but I don't really know why to do it. It's horrible. So he could not reproduce it. Then I tried to get the device, which was complicated for other reasons. But I didn't get it, but I found another way to reproduce the bug, and that was with Xamarin Test Cloud. So Xamarin Test Cloud was a service where you could submit a Xamarin app and, like, bundled with some UI tests, and then the service will test it on a couple of different Android devices, and it will send you back the results. So I hacked it a little bit and, you know, bundled it with my custom Mono Runtime to print more information, and only like almost 2 weeks later, I figured it out. So what happened? So as we have seen before, it's a system execution exception with a SIG-IL. So what is a SIG-IL? SIG-IL is a signal coming from the operating system and telling you that the CPU tried to execute an instruction that doesn't exist. So it's an illegal encoding. And IP here means that it happened at that program counter or instruction pointer, and this will be important later. So this is kind of a common thing, like as a cheat engineer, there's already a click, and it's probably related somehow to cheating. So the reason is modern CPUs are so complicated that do a lot of optimizations, and there's an instruction cache and a data cache. So why is that relevant to cheating? When you cheat, you allocate some memory, you write into it, so it will hit the data cache, and then you will try to execute it, so it will hit the instruction cache. And you have to make sure before you try to execute it that you sync those 2 caches somehow, and you just tell the caches just flush. It's called cache flushing, and it's like a common problem, and there are helpers for that, and that specific helper is in the libgcc, so from the GNU C compiler. And how it works is that you pass the memory address in there, and then the size of the region that you want to flush, and then it will do it. And so the cache doesn't work per byte, but it tries to put those things in segments. So we call it cache line size. So the cache line size on a desktop is like half a megabyte or something like that, and it's CPU implementation dependent. So that's why this method tries to be clever and caches the cache line size, and because it's something you need to request from the CPU. So it will do that on the very first time, and then it uses this cache line size to flush out each of those lines in a loop, because why not? It's like some kind of optimizations that you don't do it per byte, because that would be a waste of time, right? Okay, so what is the problem now? The problem now is this function, because the Galaxy S7 is so amazing that it has this big little architecture. What is that? It has two CPUs that are very powerful that you can use for your games, and then it has two other CPUs which are low powered, which can be used, for example, when it's switched off to fetch your emails in the background or something like that. And that will use less energy and so forth. And the problem is now that those two CPUs have two different cache line sizes. So whoever calls it first wins. And if you happen to call it with the faster CPU first, you will have a larger cache size. So it was 128 bytes, and the smaller one had 64 bytes. And now those addresses make sense, maybe. So if you think of those addresses as 64-byte buckets, the thing is, it will never happen in those two buckets because they will always be flushed out properly. It only can maybe happen on those if it was initialized wrong. Yeah, that was a fun bug. All right, and there was also a happy end. 1 month later, I got the device. So. All right, that was it. Any questions?
How do you do Swift interop now? So I reckon that some of it works using the Objective-C Swift compatibility mode, or is it really?
We have something in the pipeline. We will not go through Objective-C.
You said you have your mono error tracking. Do you create some sort of mini dump, or you do the stack walking on the client?
So usually we try to do two things. One thing is to get a managed stack dump, so all of the managed frames, and then we also try to get a native stack trace. So when a crash happens inside of the Mono Runtime, that we also know where this is coming from. Is that answering your question? Yeah. It's very platform dependent. It doesn't work the same on every platform. It's a mess. We can talk offline.
Okay.
All right. And thank you again.